together. So what are the different elements that are in this equation? CHO. Is there anything else? Okay, no. So let's go through the reactants. Like, this is the most complicated one, so let's start with carbon. How many carbons are there in the reactants? Yeah, so just 2. How many hydrogens? Oh, that's good. Yeah, check that out. There's I was totally going to go for 5 too. Very convincing. So 5 and 6. So yeah, it's 6, right? Because there's a 5 there, but there's also 1 written here. Good. How many oxygens are here?
3.
Right. There's 1 from that ethanol, and there's 2 from that oxygen. Whoops, because I can't use the shift key apparently. So that's 3. How about in the products? How many carbons? How many oxygen? I'm sorry, how many hydrogens?
2.
For a lot of you, this is review, and I really appreciate your patience.
3.
Oh, yes. 1 times 2 plus 1 times 1. So another mistake averted by the class. Thank you. So CO2 has 2 oxygens, and H2O has 1, so that's 1 times 2 plus 1 times 1, so that's 3. Okay. Pretty straightforward. Not a lot of crazy stuff. Is this balanced yet? Yeah, look, like there's 2 carbons in the reactants, but only 1 in the products. There's like 6 hydrogens, 2 in the products, 3 in the reactants for oxygen, 3 in the products. That's at least balanced. That's good. But we need to get everything balanced. So for carbon, if we have 2 in the reactants, how can we make the products have 2? Should we put a 2 in front of the water? Would that help with carbon? But it would with the CO2, right? If we had 2 CO2s, that would make it 2 equivalents of 1 carbon per CO2 molecule, so that's 2 total. Right now it's balanced in carbon. Did that change the number of oxygens? Yeah, so now I have to change that. It's a tangled web we leave when we balance equations. Did I get that right? I think so. Okay. So other stuff is not balanced. How about we balance the hydrogens? So how many hydrogens are 6? And then over here, how many do we have? So yeah, someone said multiply by 3, so let's do that. Oops. 6 total. That changes the number of O's again, right? So 3 times 1, 7. Okay. So how many oxygens? We have 3 right now. How do we make this into 7 oxygens? If we were to change this one, we change the number of carbons and hydrogens. So I don't want to change it, because then I have to change like all this other stuff again. So I'd like to give it a shot and do it with just oxygen, because it won't change anything else. It'll just change the oxygen number. O2 just has O's in it. And then my hope is it'll be nice and balanced, and I can move on to the next question. If not, then it'll be an iterative process. So let's hope and pray here. So I'm going to put 3 in front of that. So that'll give me 1 from the ethanol and 6, 3 times 2, for the O2. So that's 7. I think that's right. Maybe I should just make sure. So there's 1 and 6 is 7. Okay. And then for H's, it's 6, 6. And then for carbon, it's 2 and 2. I think we're okay. Like one example of a salt that gets broken up into ions would be table salt, sodium chloride. So water, when you dissolve salt into water, it actually breaks apart sodium from chloride. They're not really attached to each other anymore. Like there's a little bit of like attraction between plus and minus charges, but pretty much they're like loose in solution in water. And if you looked at like how much water versus a saltwater solution conducts electricity, you'd see that a saltwater solution conducts way more electricity than a regular water solution does. So there's a different sort of, I almost want to say chemical property where we're doing something here. We're changing the units, the fundamental units of those compounds. It's not like there's NaCl in solution. There's Na plus and there's Cl minus and they're in solution. There's a good picture in that last slide that shows this. So like the water will dissolve the sodium ion and the chloride ion. This doesn't happen to everything. Sugar, for example, is a great example of something that dissolves into water but does not get broken up by the water. Right? So these are all salts. They all have a positive ion and a negative ion. So, for example, potassium hydroxide, when it's in water, it dissolves into water, and it doesn't just stay as potassium hydroxide. Actually, it's been broken up into potassium ions that are surrounded by water and hydroxide, OH minus ions that are surrounded by water. All of these have that happen to them. They dissolve pretty much completely. Chemical reactions tend to be favorable, tend to proceed if if that chemical reaction increases disorder, or if it involves the release of a lot of energy. A lot of, I guess, heat is a good gauge for that. So some sort of release of energy or some sort of increase in disorder. Here's an example of a change that happens because of an increase in disorder. So things sort of mix because of an increase in disorder. There are more ways for these things to be organized together when they fill up a larger volume than when they're cooped up together. So gases will expand to fill a volume. Gases that you separated out will actually like intermingle, and this is just an increase in disorder. When you put a salt in water, the salt dissolves, and you're going to have ions in water. So let's see what you guys think. I'm curious. Lithium nitrate is lithium NO3. So this is lithium nitrate. So what do you guys think is going to be the products that form? We've got some for B. That's not good. All right. So lithium. It's a metal. It'll form an ion, lithium plus, right? In the periodic table, it's like in the first column. So that means that you're going to be forming lithium plus. Lithium is a metal that will react with water and like form hydrogen gas, just like potassium did. So this isn't going to exist on Earth for very long. You have to put it under mineral oil or something. So when you throw it into water, it's going to react. And lithium nitrate is this. Lithium nitrate consists of lithium plus and a nitrate minus. So really, there's not much going on in terms of lithium zero. Like, that's not happening. So B is a bad idea. I told you that the salt's going to dissolve, so it can't be A, right? It's not going to be lithium nitrate. It'll be lithium plus and nitrate minus. So what do we got? We got a lot of people saying D, a few people saying E. O2 minus probably not going to be happening much. Okay. I think you guys believe me. When we're thinking about solutions and we're thinking about possible double displacement reactions, the question is what combination of ions might be favored by some reason? Like, will the ions precipitate out of solution? Will they be less soluble? What's going to cause them to be favored? Precipitate means crashing out is the precipitate. That's what precipitate means. To precipitate means to have something that was in solution crash out, form a solid, make some yucky stuff on the sides of the flask. That's what precipitate means. When I'm thinking about potassium chromate, it's not potassium chromate together as like one compound that doesn't break up. It's potassium ions and chromate ions in water solution. And here we have barium ions and nitrate ions. And the question is, what products would they form? Well, if they form any products, it's going to be because they come out of water. Somehow they're being favored to come out of water. And if that's the case, we can at least give a series of combinations of possible products that would form. So possible products might be K2CrO4 2-. It might be barium nitrate. It might be switching partners, so like potassium nitrate. It might be barium chromate. Any of these things might be favored. We have to come up with some sort of rules or something to look up that we can figure out which one would be favored or which one would precipitate. So this is just showing like how you can come up with different potential products. So those same ions are just saying, okay, positive ions, negative ions, how can we combine them? These are possible products. I don't know which one's going to form. Let's find out. These are the original reactants. So if these were the ones that were favored, we would say there's no reaction. And if either of these is favored, we'd say that there's a product. So how do we know which one is actually going to be produced? Well, it depends on which one is going to precipitate out. You don't have to memorize them, but you have to be able to look them up in a book and use them. Basically, the idea is, hey, if one of these products, these possible products, is really not soluble in water, it'll precipitate out, and that's the product. Yeah, alkali metals are those first row of metals. So potassium chromate is soluble, but barium chromate won't be. So barium chromate is going to precipitate out. So in this list of possible products, this is going to precipitate out. So that means that what will be left in solution is this. So you would say actually that if I wrote a reaction, I should probably start using Twidless. I don't have to use the board. I don't know. You guys don't seem to care. Potassium nitrate? Yeah. No, potassium chromate plus barium nitrate. That's a question mark. K2NO3. Nope. KNO3. Am I doing this right? So far, so good. Plus BaCrO4. So the question is whether or not, if we put these things in solution, will they form these or not? Will these ions that have been separated out in solution magically know to do this? And in fact, they do, because this comes out as a solution. So this just leaves the solution. It becomes some ugly yellowish white precipitate on the bottom. And you can filter this out. And what it leaves in solution in water are potassium ions and nitrate ions. So this reaction is favored by the solubility, or I guess lack of solubility, of barium chromate.